Hello viewers, welcome to the channel Amazing Civil Engineering Studies. Here we will learn about different concepts related to civil engineering. Time to enter the world of civil engineering. Please subscribe to the channel and press the bell icon for more new updates. In today's video we are going to discuss about Introduction to Fluid Mechanics. Definition of a fluid. A fluid is defined as a substance that deforms continuously under the action of a shear stress, however small magnitude present. It means that a fluid deforms under very small shear stress, but a solid may not deform under that magnitude of the shear stress. By contrast, a solid deforms when a constant shear stress is applied, but its deformation does not continue with increasing time. In above figure, a shear force F is applied to the upper plate to which the solid has been bonded. A shear stress resulted by the force equals to tau equals, where A is the contact area of the upper plate. We know that in the case of the solid block the deformation is proportional to the shear stress T provided the elastic limit of the solid material is not exceeded. In short, a fluid continues in motion under the application of a shear stress and cannot sustain any shear stress when at rest. About fluid mechanics. Fluid mechanics is the study of fluids and the forces acting on them. Fluids include liquids, gases, and plasmas. Fluid mechanics can be divided into fluid statics, the study of fluids at rest. Fluid kinematics, the study of fluids in motion, and fluid dynamics, the study of the effect of forces on fluid motion. It is a branch of continuum mechanics, a subject that models matter without using the information that it is made out of atoms, that is, it models matter from a macroscopic viewpoint rather than from a microscopic viewpoint. This study area deals with many and diversified problems such as surface tension, fluid statics, flow in enclosed bodies, or flow round bodies, solid or otherwise, flow stability, etc. For example, various aircrafts and rocket engines involve fluid flow fields, reaction forces. In the food and chemical process industries, fluid mechanics is required for the design of transport system and in process design. In fact, almost any action of a person is doing involves some kind of a fluid mechanics problem. What is fluid flow? Fluid flow is a part of fluid mechanics and deals with fluid dynamics. Fluids such as gases and liquids in motion are called fluid flow. It involves the motion of a fluid subjected to unbalanced forces. This motion continues as long as unbalanced forces are applied. For example, if you are pouring water from a mug, the velocity of water is very high over the lip, moderately high approaching the lip, and very low at the bottom of the mug. The unbalanced force is gravity, and the flow continues as long as the water is available and the mug is tilted. Different properties of fluids. Though each fluid is different from others in terms of composition and specific qualities, there are some properties which every fluid shares. These properties can be broadly categorized under kinematic properties. These properties help in understanding the fluid motion. Velocity and acceleration are the kinematic properties of the fluids. Thermodynamic properties. These properties help in understanding the thermodynamic state of the fluid. Temperature, density, pressure, and specific enthalpy are the thermodynamic properties of the fluids. Physical properties. These properties help in understanding the physical state of the fluid, such as color and odor. Properties of fluid. Some of the basic properties of fluids are discussed below. Density. The density of a substance is its mass per unit volume. In fluid mechanics it is expressed in three different ways. Mass density, specific weight, relative density. Mass density. Mass density is the mass of the fluid per unit volume. Equals mass of fluid volume of fluid unit kilogram per cubic meter, kg/3. Typical values. Water 1000 kg/kilogram per cubic meter. Air 1.23 kg/kilogram per cubic meter, at standard pressure and temperature, STP. Specific weight. Specific weight, W, as we express a mass m has a weight W equals mg. The specific weight of the fluid can be defined similarly as its weight per unit volume. Specific weight is defined as the weight possessed by unit volume of a fluid. Specific weight is dependent on acceleration due to gravity as it changes from place to place. W equals times times unit Newton per cubic meter, N/m3. Typical values. Water 9.810 N/Newton per cubic meter. Air 12.07 N/Newton per cubic meter, at standard pressure and temperature, STP. Relative density, specific gravity. Relative density, specific gravity, S. Specific gravity is the ratio of fluid density. Specific weight, to the fluid density, specific weight, of a standard reference fluid. For liquids, water at 4 degrees Celsius is considered as standard fluid. S. Liquid equals liquid. Water at 4 degrees Celsius. Similarly, for gases, air at specific temperature and pressure is considered as a standard reference fluid. S. Gas equals gas. Gas at STP. Units, pure number having no units. Typical values. mercury 13.6 water 1. Specific volume. In fluid mechanics, specific volume is the reciprocal of density. It can be expressed as the volume that a fluid occupies per unit mass. Specific volume of a fluid is mean volume per unit mass, i.e. the reciprocal of mass density. Specific volume V equals volume of fluid, mass of fluid equals. Typical values. Water 10331 cubic meter per kilogram. Air 1.23 times 10331. Specific volume is denoted by V. SI unit of specific volume. 31 cubic meter per kilogram. Viscosity of liquid. Viscosity is defined as the property of a fluid which offers resistance to the movement of one layer of fluid over another adjacent layer of fluid. When two layers of a fluid, a distance apart, move over one another at different velocities, the viscosity together with relative velocity causes a shear stress acting between the fluid layers. The top layer causes a shear stress on the adjacent layer while the lower layer causes a shear stress on the top layer. This shear stress is proportional to the rate of change of velocity. It is the measure of resistance to the flow of fluids. The viscous force is due to the intermolecular forces acting in the fluid. The flow or rate of deformation of fluids under shear stress is different for different fluids due to the difference in viscosity. Fluids with high viscosity deform slowly. It is denoted by the symbol equals, where mu is the constant of proportionality and is known as the coefficient of dynamic viscosity or only viscosity. Represents the rate of shear strain or rate of shear deformation or velocity gradient. Equals. The viscosity is also defined as the shear stress required to produce unit rate of shear strain. Units of viscosity. In MKS system, unit of viscosity equals CGS unit of viscosity, also called poise, equals SI unit of viscosity equals Newton second per meter square, NSM2, or Pascal seconds, PaS, or kgm1s1. Kinematic viscosity. It is defined as the ratio between the dynamic viscosity and density of fluid. It is denoted by the Greek symbol, called nu. Thus, equals viscosity density equals. In MKS and SI, the unit of kinematic viscosity is /SEC, meter square per second. While in CGS units, it is written as /SEC in CGS system. Kinematic viscosity is also known as Stoke. 1 Stoke equals 1/SEC. Dynamic viscosity, m, equals. It is the measure of internal resistance of fluid considering the external forces which causes the motion of fluid. Amount of force required to make the fluid flow at the velocity of 1 ms, where the ability of the fluid is determined by the force it can withstand. Examples: fluid used in hydraulics, lubricants to avoid friction, bearings, seals, etc. Shear stress, force F/moving plate area A, shear rate, speed V/liquid film thickness H, usually written as Fa equals mv/h. It is measure of fluid's resistance to shear flow when some external force is applied. It is useful for describing the behavior of fluids under stress. Mainly, it is useful in describing non-Newtonian fluids by observing how viscosity changes as the shear velocity changes. Summarizing the difference between these two. We denote dynamic viscosity as Greek letter μ and kinematic viscosity as nu. Their units are different. For dynamic viscosity it is ns/. For kinematic viscosity it is /s. If you notice words dynamics and kinematics and know their respective meanings, in viscosity units you will see that force is considered for dynamics, which justifies the word dynamics, and for kinematics it is not. They both are equally useful for measuring viscosity for Newtonian and non-Newtonian fluids. But, kinematics viscosity is considered and measured first for substance and then its dynamic viscosity with the help of density. Kinematic viscosity results are dependent on density of fluid, whereas for dynamic viscosity it is not. Also, temperature at which viscosity is measured plays an important role while measuring viscosity for both. Also, if for two different fluids, their dynamic viscosity is same, their kinematic viscosity can be different. Newton's law of viscosity. It states that the shear stress on a fluid element layer is directly proportional to the rate of change of shear strain. The constant of proportionality is called the coefficient of viscosity. The ratio of shear stress to shear rate is a constant, for a given temperature and pressure, and is defined as the viscosity or coefficient of viscosity. Fluids which obey the above relation are known as Newtonian fluids, and the fluids which do not obey the above relation are called non-Newtonian fluids. Consider a flow in which fluid particles move in a particular direction maintaining straight, parallel lines. For considering viscosity, Newton proposed some fundamental assumption. He proposed that firstly, when a flow is adjacent to surface, stick to it and have zero velocity relative to the boundary, which is called no-slip condition. Other fluid particles attempting to slide over them are retarded because of an interaction between faster and slower moving fluid, a phenomenon that gives rise to shearing force. Secondly, shear stress on an interface tangent to the direction of flow is proportional to distance rate of change of velocity. Equals. Where equals viscosity equals shear stress equals F/A equals rate of shear deformation. μ is called coefficient of viscosity. It can be considered as modulus of rigidity of fluid. Fluids who obey Newton's viscosity law is Newtonian fluids. Compressibility: when pressure is applied on a fluid, its volume decreases. This property of a fluid is called compressibility. Elasticity: when the force generating the pressure on the fluid is released, it returns to its original volume. This property of a fluid is called elasticity of the fluid. Vapor pressure: molecules of a liquid escape from its surface to fill the space above the liquid surface and the container until such time when the pressure due to these molecules above the liquid surface reaches the vapor pressure of the liquid. This is how the vapor pressure of a liquid is defined. Surface tension: it is often observed that a drop of blood forms a hump on a horizontal glass, a drop of mercury forms a near-perfect sphere and can be rolled just like a steel ball over a smooth surface. Water droplets from rain or dew hang from branches or leaves of trees. A liquid fuel injected into an engine forms a mist of spherical droplets. Water dripping from a leaky faucet falls as spherical droplets. A soap bubble released into the air forms a spherical shape, and water beads up into small drops on flower petals. In these and other observances, liquid droplets behave like small spherical balloons filled with the liquid, and the surface of the liquid acts like a stretched elastic membrane under tension. The pulling force that causes this tension acts parallel to the surface and is due to the attractive forces between the molecules of the liquid. The magnitude of this force per unit length is called surface tension S and is usually expressed in the unit N/m. This effect is also called surface energy. In this case, S represents the stretching work that needs to be done to increase the surface area of the liquid by added amount. Cohesive forces are the forces that exist between molecules of one phase. Adhesive forces are the forces that exist between molecules of two different phases. Surface tension: the molecules on the surface of a liquid, that is, the interface between the liquid and the air, are bound together by a weak force called surface tension. This force makes the liquid form a layer and is caused due to the cohesive force between the molecules of the liquid. Capillarity: the molecules of a liquid have two types of forces acting on them. One is cohesive force, the force among the molecules of the liquid only, and the other one is adhesive force, the force acting between the molecules of the liquid and some other substance. When the adhesion between the liquid and the container wall is more than the cohesion among the liquid molecules, the liquid sticks to the container walls and this results in capillary rise. The opposite of this behavior happens when the cohesion is more than the adhesion, the capillary level dips. Types of fluids based on viscosity. The fluids may be classified into following 5 types. Ideal fluid, real fluid, Newtonian fluid, non-Newtonian fluid, ideal plastic fluid, incompressible fluid, compressible fluid. Ideal fluid. A fluid which is incompressible and is having no viscosity, is known as ideal fluid. Ideal fluid is only an imaginary fluid, as all the fluids which exists have some viscosity. A fluid is said to be ideal when it cannot be compressed and the viscosity doesn't fall in the category of an ideal fluid. It is an imaginary fluid which doesn't exist in reality. Real fluids. A fluid which possesses viscosity is known as real fluid. All the fluids in actual practice are real fluids. All the fluids are real as all the fluid possess viscosity. Newtonian fluids. Aerial fluid in which the shear stress is directly proportional to rate of shear strain, or velocity gradient. When the fluid obeys Newton's law of viscosity, it is known as a Newtonian fluid. Non-Newtonian fluid. Aerial fluid in which the shear stress is not proportional to the rate of shear strain. When the fluid doesn't obey Newton's law of viscosity, it is known as non-Newtonian fluid. Ideal plastic fluid. A fluid in which shear stress is more than the yield value and shear stress is proportional to the rate of shear strain, or velocity gradient. When the shear stress is proportional to the velocity gradient and shear stress is more than the yield value, it is known as ideal plastic fluid. Incompressible fluid. When the density of the fluid doesn't change with the application of external force, it is known as an incompressible fluid. Compressible fluid. When the density of the fluid changes with the application of external force, it is known as compressible fluid. Below is the tabular representation of the fluid types. Types of fluid. Density. Viscosity. Ideal fluid. Constant. Zero real fluid. Variable. Non-zero Newtonian fluid. Constant/variable. T equals U. Non-Newtonian fluid. Constant/variable. T is not equal to U. Incompressible fluid. Constant. Non-zero/zero compressible fluid. Variable. Non-zero/zero. Types of fluid flow. Compressible and incompressible flows. Laminar and turbulent flows. Steady and unsteady flows. Uniform and non-uniform fluid flow. Rotational and irrotational fluid flow. 1, 2, and 3-dimensional fluid flow. Compressible and incompressible flows. An incompressible flow is a flow in which the variation of the density within the flow is considered constant. In general, all liquids are treated as the incompressible fluids. On the contrary, flows that are characterized by a varying density are said to be compressible. Gases are normally used as the compressible fluids. However, all fluids in reality are compressible because any change in temperature or pressure result in changes in density. In many situations, though, the changes in temperature and pressure are so small that the resulting changes in density are negligible. The mathematical equation that describes the incompressibility property of the fluid is given by equals 0, where is the material derivative defined by equals plus plus, in which represents velocity of flow and is the vector differential operator. Steady and unsteady flows. A steady flow is one for which the velocity does not depend on time, in which the fluid characteristics like velocity, pressure, density, etc. at a point do not change with time. In which the fluid velocity, pressure, or density at a point changes with respect to time. When the velocity varies with respect to time, then the flow is called unsteady. Laminar and turbulent flows. Laminar flow, streamlines, is one in which each fluid particle has a definite path. In such flow, the paths of fluid particulars do not intersect each other. In turbulent flow, the paths of fluid particles may intersect each other. Consider water flowing through a pipe at low speeds. There is an smooth condition, which is called laminar flow. The mixing of warm and cold air in the atmosphere by wind, which causes clear air turbulence experienced during airplane flight, as well as poor astronomical seeing. Fluid pressure and Pascal's law in fluid mechanics. Fluid pressure and Pascal's law are explained briefly by considering a small fluid element that is in the state of rest. The concept is more elaborated with the help of a workout example. Fluid pressure at a point. The fluid pressure acting at a point can be given by the formula P equals F/A, where F is the force acting on the fluid over an area A. Considering a small area d in the fluid, the force acting on the area d of this fluid in the state of rest is in a direction perpendicular to the surface d. If dF is the force acting perpendicular to the surface of d, then pressure acting on a point in a fluid at rest is given by P equals dF/d. Units of fluid pressure. The fluid pressure can be measured either in m.k. units or in SI units. In m.k. units, pressure is measured in kgf/ or kgf/. In SI units, the fluid pressure is measured in n/ or n/. Note, 1 n/m2 equals 1 pa, 1 bar fluid pressure equals 100 kilopascal equals 100,000 pascal equals 100,000 n/m2. What is Pascal's law? Pascal's law states that the intensity of pressure at a point in a static fluid is equal in all the directions, x and z directions. This is proved by the following derivation. Consider an arbitrary fluid element ABC with sides AC, AB, and BC as dx. dy, and ds. Here, the width of the element is taken as unity. Let px, pi, and pz be the pressure intensities acting on the surfaces ABC and BC. Let the angle ABC be Q. The whole fluid system is illustrated in the figure. The forces acting on the fluid element are the pressure forces on the faces of the element, the weight of the whole fluid element acting in the vertical direction downwards. 1. Pressure forces acting on the element. Force acting on AB equals px dot area of the face AB equals px. dy. 1. Force acting on AC equals pi area of the face AC equals px dx. 1. Force acting on BC equals pz area of the face BC equals pz ds. 1. 2. Weight of the fluid element. Weight of the fluid element is given by W equals mass of fluid element xg equals volumes density of fluid, GW equals ab xac / 1 density of fluid g. By resolving the forces in x direction equals px dysprosium 1 pz dot ds. 1 dot sin 90 q equals 0 equals px dysprosium 1 pz dot ds dot cos q equals 0. From figure, ds cos q equals dy equals px equals pi. Equation number 2. Y direction pi dot dx. 1 pz dot ds. 1 dot cos 90 q dx dot dy / 2.1 dot density dot g equals 0. Here also, cos 90 q equals sin q, and the weight is neglected as the element is very small. Hence we get pi equals pz. Equation number 3. From equation 2a and d3 it is proved that px equals pi equals pz. The above equation states that the pressure at a point on a fluid in rest are equal in all direction. Workout example. Consider a hydraulic press with a ram of 0.3 m diameter and a plunger of 4.5 cm diameter. If the force applied at the plunger is 500 N, determine the weight lifted by the hydraulic press. Solution, given data. Diameter of ram equals 0.3 m. Diameter of plunger equals 0.045 m. Force on plunger, F equals 500 N. Weight lifted equals. From the figure, a force is applied at the plunger in order to lift a weight W at the other end of the hydraulic press. The system here follows Pascal's law. As per the law, the stress created at the point of force applied, at point A, is equal to the stress created at point B. Then, 1 stress at point A equals Pa equals force area equals Pa equals force plunger area equals 500 / 3.124 x 0.045 x 0.045 / 4 equals 314465.4 n / m22. Pressure intensity at B equals PB equals force / area of ram equals PB equals Pa, as per Pascal's law. equals PB equals 314465.4 equals force/area of ram. Force or weight lifted equals 314465.4 x area of ram equals 314465.4 x 3.14 x 0.3 x 0.3/4. Force or weight lifted equals 22222 N equals 22.2 kN. Pressure variation in a fluid at rest, hydrostatics. The three fundamental principles for the variation of static pressure P throughout a body of fluid at rest are: A. The pressure at a point is the same in all directions, Pascal's law. B. The pressure is the same at all points on the same horizontal level, and C. The pressure increases with depth z according to the hydrostatic equation. dP dz equals ρg for a fluid with constant density ρ. The increase in pressure over a depth increase h is ρgh, a result which can be used to analyze the response of simple barometers and manometers to applied pressure changes and differences. Hydrostatics law states that rate of increase of pressure in a vertically downward direction in fluid/liquid is directly proportional to weight density, i.e. height of column of the liquid. The hydrostatic pressure is the pressure exerted by a fluid at equilibrium at any point of time due to force of gravity. Fluid pressure can be caused by gravity, acceleration, or forces when in a closed container. If we consider the layer/column of water on the top of a bottle, the pressure exerted by the layer/column of water acts on the container at the sides, the surface of air on top and the layer of water at the bottom. As we move down from the top of the bottle to the bottom, the pressure exerted by the top layer/column on the bottom adds up. Due to this phenomenon, the fluid at the bottom of the container experiences more pressure than the fluid which is above it. Units and scales of pressure measurement. Pascal, N/m², is the unit of pressure. Pressure is usually expressed with reference to either absolute zero pressure, a complete vacuum, or local atmospheric pressure. The absolute pressure, it is the difference between the value of the pressure and the absolute zero pressure. P. Absolute equals P0 equals P gauge pressure. It is the difference between the value of the pressure and the local atmospheric pressure, P. Atmospheric P gauge equals PP. Atmospheric vacuum pressure, if P. Atmospheric, then the gauge pressure, P. Gauge, becomes negative and is called the vacuum pressure. But one should always remember that hydrostatic pressure is always compressive in nature. See figure. Figure showing relationship between pressure. At sea level, the international standard atmosphere has been chosen as P. Atmospheric equals 101.32 kN m². Thank you for watching. In next video we will learn about pressure measurement.
Thank you for watching. Please subscribe to the channel and press the bell icon.